Hello, I'm Terezinha Nunes, and I'm very happy to be presenting these ideas that come from my research, as I mentioned at the end of Module 0, and the research of many other people who have helped me to reach some understanding of how children learn mathematics. But I thought I would be starting not from the very beginning of my professional life, but from a study that marked everything that I did since. And that was the work on street mathematics. So the main themes in this module will be why we started to do the work in street mathematics, was what we thought about children really true, and then we did the second study in order to investigate street mathematics in greater detail. Now, the reason we started this research is that there were debates going on intelligence and socio-economic background. There were many researchers arguing that children from lower socio-economic backgrounds performed worse in school than children from better socio-economic backgrounds because they just were not as intelligent. Whereas other researchers thought that that wasn't the case. So the school performance of children and adolescents from working class backgrounds in school was a very hot topic. We thought about it, and our personal knowledge of children and adults engaged in the informal economy in Brazil was at odds with the idea that they were not able to do mathematics. My colleagues, Ana Lucia Schliemann, David Carraher, and I sought to analyze if the personal knowledge that we had of these children and adolescents in the informal economy being very apt at doing mathematics computations, and in spite of that, failing in school, was correct. In fact, were these different children, the ones who worked in the informal economy and the ones who failed in school, or were they the same children who were just succeeding in the informal economy and failing in school? Now, we didn't know how to research this, and we sought inspiration in the methodological approach used by Michael Cole and Gay in the study of the new mathematics in an old culture in Liberia. We did what they did in order to start these studies. So first, we went to the markets and we bought things from the children, and we gave them money to pay for the things, and we asked them how much our purchases would cost and how much change we would get. We recorded these interactions with their permission and their parents' permission, because they often walked alongside their parents in the street markets. And then we went back and transcribed what had happened and analyzed what had happened. In particular, we wanted to know what computations they had done and how they had done them. We then went back to the street markets and we told the children and their parents that we wanted to understand how the children were so good at calculating, and we got their permission to give them new problems. But in fact, the problems were not new. They were the same problems that the children had solved previously, except that we now presented them as word problems, the way they are presented in school, or as simple computation exercises. The video that you will see next was done by the Open University, and it records how the children seem to be completely able to solve computations in the street markets and how they seemed completely unable to solve the same computations when they were trying to do it the way they did it in school. And this video is presented with permission from the Open University and with thanks for their permission.
Vamos somar aí 250 mais 800 e mais 600. Agora você vai fazer essa soma para mim, tá? Por escrito. Vê se você sabe fazer. Sabe não? Na cabeça como é?
Na cabeça?
Sim. 1,65. E aí, vamos ver se a gente sabe. Como é que a professora manda fazer? 0 com 0, quanto é que dá?
Now, I hope you got the same sense of awe that we got when we first observed this phenomenon. The same children looked both able and unable to carry out the same arithmetic operations. And we didn't just work with one child, we worked with 5 different children, and we presented to them a total of 65 computations in the school-like situation and in the market situation. Now, in the market, in the street market, they had 98% correct responses. In the word problems that we presented to them, their percentage of correct responses was equal to 74. And in the computation exercises, they only got 37% of the answers correct. Well, this finding just blew our minds because, after all, they were the same children. So the idea that the same children could look able and unable to do the exact same mathematical task was one that we could not explain at that time. Now, an undeniable difference between the way the children solved the problems in the streets and they solved the problems in school was the system of signs they used. And by systems of signs, I'm talking about the kinds of numerical systems they used. In the streets, in the formal economy, they always solved the problem orally. And when I say orally, I mean orally. I'm not saying mentally, because they talked as they solved the problems. In the arithmetic operations, they almost all the time used the written algorithms that they had been taught in school. Now, why do I say oral and not mental? Because both in oral and written arithmetic, you have to use mental resources, a point to which we'll come later on. Now, there are some unspoken rules about the use of oral or written arithmetic. In the informal economy, the vendor counts out the money orally as they give it to the customer, and it is part of making sure that they both know that the change is correct. In schools, teachers often insist that the children write as they calculate because the teachers expect, looking at the written productions of the children, they will be able to see whether the children were reasoning correctly. Now, there was something very interesting about the reaction to these studies once it was published. And many people thought that this was all due to the fact that in the informal economy, we were in a social context that differed from the school context. So we decided to simulate street mathematics in school. We did a second study in which we saw the children always in school, but we asked them to solve problems in 3 different conditions. One condition was a pretend shop, so we would say to the child, you have some pencils to sell, and I'm going to pay you with 100 Carraher note. How much is the change going to be? In the oral story problems, we would use the same numbers, but they would not be about the informal economy. They might have been, for example, there are so many classes of first grade in the school and so many children in the first grade. How many children in first grade in the school? And in the computation exercises, we simply told the children the number and asked them to tell us the answer. If the simulation of the shop worked in the pretend shop, we should actually elicit quite a lot of oral arithmetic, and that would allow us to understand street mathematics and school mathematics better. Now, there were alternative hypotheses we had about what might happen. If the children performed better in the street markets because they had a different relationship to the researchers, then their performance in a simulated shop in school should drop. They should now perform the same way they perform across the 3 conditions. If the children were concrete thinkers, and that's what some people said, they performed better in the informal economy because they had the objects and the money and they were concrete thinkers. If that were the case, then in a simulated shop where they didn't have objects and they didn't have money, their performance would again drop. But if our observation was correct, that the systems of signs that they used to think with, oral numbers in the street markets and written numbers in the school-like situation, if that hypothesis was correct, and if we could elicit oral arithmetic in the simulated shop, then the differences in performance should continue. So we were quite curious to see what was going to happen. And what I'm going to show you next is the result of this investigation. As you can see in this slide, the percentage of correct response in the simulated shop, in the word problems, and in the computation exercises was very similar. When the children used oral arithmetic, they were systematically better than when they used written arithmetic. So this finding is actually much less well known and much less discussed in the literature, but it was a crucial finding for us. What it showed us was that the difference in the children's performance when they were in the informal economy and when they were solving computation exercises was not explained by the social situation in which they found themselves, but it was actually explained by what we call a tool for thinking. And the tool for thinking in the street markets was typically oral arithmetic, and the tool for thinking in schools was typically written arithmetic. Now let's think about a problem, an example of how the children solved the computation in oral arithmetic. So the problem we asked this child to solve was 252 minus 57. And that was actually presented as a computation, not in the simulated shop. And this particular child said, take away 52. Now what the child is doing is taking away 52 both from 252 and 57. because the child goes on to say, that's 200 and 5 to take away, and that is now a very easy problem. That's 195. If you want to enjoy many other numbers, many other examples, you would need to read the research. Now, when we listen to the children thinking using oral arithmetic, there are two things that are very interesting. One is that in oral arithmetic, the children make explicit reference to the values. So the child says 200 when referring to the 2 in the place of hundreds. And when they calculate, they go from larger to smaller. So they typically take away the tens before they take away the units. Now let's see an example of the taught algorithm that this child would have used if the child were solving the problem like it's solved in school. So the child would have to say 252, so I try to do 2 minus 7. You can't do that, so you borrow 1, and now you do 12 minus 7, 5. And if you listen to me, when I borrow, I say I borrow 1, but it's actually borrowing a 10. And that is typical of written arithmetic. We talk about digits. So the system of signs used is based on writing and not on the quantities that the writing represents. In the subtraction, we see 2 instead of 200, and in written arithmetic, we proceed from smaller to large. So we start with units, and then we calculate the tens, and then we calculate the hundreds. Now, in spite of these big differences on how the children calculate, there are very basic similarities in the underlying logic. Both in oral arithmetic and in written arithmetic, the assumption is that any number can be broken up into parts, and we can calculate separately on the parts and then put the number back together again. Gérard Vergniaud used the terminology a theorem in action. So if we ask the children, why do you do the calculation in this way? Because they will say, because it's obvious, because it's logical, but they wouldn't be able to use the terminology, the additive composition of number or the associativity of addition and subtraction. But these are the theorems in action, implicit in the way the children solve both oral and written arithmetic. And in fact, in the school-taught algorithms, we use the same properties, but we don't actually teach children the terminology of additive composition and associative property of addition and subtraction. Because in our studies, the children who looked both able and unable to solve the computations were exactly the same, we cannot explain the school performance of the children from lower socio-economic backgrounds as being due to a lack of mathematical skills. Clearly, the children had mathematical skills, and schools were not harvesting those mathematical skills. I would like you to see an example of how this was so clear when you work with the same children trying to solve a computation in oral arithmetic or written arithmetic. And this is again an example from a film produced by the Open University, and I'm very grateful to them for granting permission for this film.
4th grade, where you might expect a 10-year-old to be. He uses decomposition.
850.
Certo, como é que você achou?
Eu fui assim, 500 com 200, 700. 80 com 70, 150.
Certo.
850.
Certo. Aí, se você fosse pagar para uma pessoa 850 com uma nota de 1.000, qual era o seu troco?
150.
E como é que você sabe?
Porque 850 com 50, 900. Com 100, 1.000.
Ótimo. Agora vamos ver essa coisa.
Then Moises is asked to do the same sums on paper, in the way he's been taught at school.
580 com 270.
Com 270.
Quanto é que vai dar isso? Faça como faz na escola.
He gets this one right.
Faça
Then
agora
comes the
1.000
subtraction.
menos 850. Conta de menos.
1.000.
1.000
É 3 0, não é 1.000?
é. E você vai tirar desse 1.850.
850.
Moises comes to grief here on what's known in the literature as a pedagogical obstacle. He's been taught that you can't take a big number from a smaller one, the 8 from the 1 in the lower sum. So he does it the other way round, taking the 1 from the 8, getting what he knows is the wrong answer.
Now, this example is absolutely fascinating because it shows how the tool, oral arithmetic, controls the child's reasoning. Even though it's the same child, the child cannot get the subtraction right when the child is trying to do it using the written algorithm. I have focused so far on the logic of addition and subtraction, but it's important to show some examples of oral multiplication because they also involve the same logic when the calculation is done orally or when it's done in writing. So here's a case which has attracted a lot of attention, this particular example. So I was buying coconuts from this child in the street market, and I want to mention to you that at the time the inflation in Brazil was 2,000% a year. So you didn't sell coconuts 2 weeks in a row for the same price. So the children had to actually calculate every time when they were answering questions by customers. The second thing I'd like to point out to you is that most people buy 1 or 2 coconuts. And what we did in order to elicit the children's computations was to buy an unusual number of items. So this child was selling coconuts for 35 reais, which was the Brazilian currency at the time, and each coconut, as I said, cost 35, and I said, I want 10 coconuts. How much is that? Now, what's amusing about this example is that teachers teach children in Brazil to just add a 0 at the end when they multiply by 10. But this child did all the thinking effort. The child thought about it and said, 3 coconuts will be 105, with 3 more, 210. Then the child stopped and said, I need 4 more. That is 315. I think it's 350. If you attempt to infer the child's reasoning from what the child is saying, it's really quite an interesting reasoning to follow. The child creates a group of 3 coconuts, 105, which is very easy to add. And then the child says 3 will be 105, with 3 more, 210. And the next step is with 3 more, 315, and then the child adds 35. The logic that the child is using is the distributivity of multiplication with respect to addition. And that is the same logic that we use when we carry out multiplication using a written algorithm. This same logic can be used in division, And I chose an example of oral division in a situation that was a word problem. So the problem the child was asked to solve was, I have 75 marbles to be distributed to 5 boys fairly. How many marbles does each one get? And you can almost see the child's reasoning when the child says, if you give 10 marbles to each child, that will be 50 marbles that you've already shared. And there's 25 left over to distribute to 5 boys. So he thinks about it and says, that's 5 more each, that's 15 marbles each. I'm sure you can see how the logic used in oral division is the distributivity of division with respect to subtraction. So as the marbles are given away, they are subtracted from the total. So the logic of oral multiplication and division is the same logic of the algorithms. There is one more aspect of this logic that is important to bring up, and that's the inverse relation between operations. In oral arithmetic, the inverse relation between addition and subtraction, for example, is a theorem in action, using Vergniaud's terminology. So the child wouldn't be able to say, this is why I can perform the calculation in this way. But the child understands that taking out a part of the number, doing a simpler calculation and putting it back does not alter the value, in the case of a subtraction, the value of the minuend. For example, in a subtraction where we ask the child to subtract 75 from 243, the child said, well, just give me 100 minus 75 is 25, and then you add back the 143 that you didn't give me. So the inverse relation between addition and subtraction is clearly being used as a theorem in action. And this is also used in the written algorithms. When you borrow 110 to add to the units, the value of the minuend is still the same. You're just writing the number differently. Now, what our studies of children's arithmetic in the informal economy showed is that the children were very apt to solve problems and computations in the informal economy, but they failed in school because they tried to use a different system of science which they didn't master as well. My good friend, Ubiratan D'Ambrosio, wrote extensively about this phenomenon, which he called ethnomathematics. Now, in the specific studies that Ubiratan did, he was looking at a particular group of people using a particular system of science and creating a particular form of mathematics. And this is what he called ethnomathematics. I would suggest that street mathematics is probably not a form of ethnomathematics because we don't have an identifiable group of people. There are many different people engaged in the informal economy in many different situations, and they do not use a specific system of science. They use the same oral and written numbers and the same properties of numbers that we use in school. So, what are the educational implications of these findings? This is what people asked me all the time when these studies were published. Well, I think the first major implication is something I have already mentioned in the conclusions, that we could not attribute the children's failure in school to a lack of ability. These children are clearly able to reason about numbers and about mathematics. So the major education implication, in my view, is that the theory of mathematics teaching that we had at the time was not good enough. The didactical idea that you first teach children how to solve computations and then you teach them how to apply these computations to practical situations does not fit with the results that the children are better at solving applied problems than at solving computations. In fact, it's quite clear from these results that computations are a different kind, involve a different kind of skill. The main alternative theory to that idea was proposed by Freudenthal, and his idea was that the best way to teach children mathematics was to help them to think about situations, applied situations, and help them mathematize these situations. And he always insisted that the arithmetic operations are abstractions that have been constructed over centuries. And these arithmetic procedures cannot be the starting point for learning if it took humans many years to develop these procedures. There are some references to the work that I have mentioned, and I just want to try to whet your appetite so that you go and look at Module 2. The Module 2 main themes will be about quantitative reasoning developed outside school and not about specific forms of arithmetic. So thank you, and you can now proceed to Module 2.